Before we go on to details of the generalized linear model, it will be a good idea to review the concepts of likelihood-based inference. Now, you have already studied some concepts of inference and some principles, such as, for example, the MVUEs and the blues. Now, MVUEs rarely exist outside some relatively simple settings. However, a ready tool which we always have available whenever we are able to specify a parametric distribution, and in some cases even beyond this, is the technique of maximum likelihood. The popularity of maximum likelihood estimators comes from the fact that they have some desirable statistical properties, especially in asymptotic situations. We shall look at the asymptotic properties of these estimators and also look at some common inferential procedures which are available automatically the moment we specify a likelihood. Learning objectives for this module. We shall first define the concept of a likelihood. Next, we shall look at some of its properties. Having done this, we will look more closely at the multinomial likelihood which we shall use in several applications in this paper. And finally, we shall revisit the well-known chi-squared test of fit and see that it is a special case of Wald's test applied to the multinomial likelihood. Maximum likelihood estimation is a very popular technique in statistical inference. Now, you have looked at several alternative methods for deriving estimators and for performing statistical inference. For example, you have looked at UMP tests, and you have also looked at estimators such as blues for the linear model and the MVUE for general inference. In many situations, these estimators will not exist. However, maximum likelihood estimation offers an attractive alternative. The maximum likelihood estimators can be seen to have desirable properties. Note that most of these properties are asymptotic. Maximum likelihood estimators can, however, suffer from some drawbacks in case of finite samples. In this paper, we shall mostly be concerned with large samples and assume that the asymptotic properties of the maximum likelihood estimators hold. Note, however, that finite sample inference techniques have also been worked out for GLNs but are beyond the scope of this paper in this case. A second desirable property of maximum likelihood estimators is that there is an underlying general theory which, the moment we are able to specify the likelihood, leads to standard errors in their estimators and associated testing procedures. The downside is that all this comes at a price, that is, we are required to make strong distributional assumptions. Consider a very simple example where we flip a coin 10 times. And suppose that we observe the sequence HH, T, HH, H, TT, HH. Now, it is quite simple to show that the probability of this outcome, given that the probability of heads is pi, can be given by pi to the power 7 into 1 minus pi to the power 3. This is a function of pi given the data. Our definition of a likelihood function is that in any given situation, the likelihood function is also equal to the corresponding probability mass function or the density function. However, rather than viewing it as a function of the parameter, conditional on the data, we reverse this and consider it as a function of the parameter fixed on the data. So the likelihood function in this case is given by L of pi given the observed data, and numerically it is equal also to pi to the power 7 into 1 minus pi to the power 3. The critical difference is that it is now a function of pi. In a loose sense, the likelihood is the probability of observing the given data for a particular value of the parameter, and we shall choose that value of the parameter which will maximize this probability. Here is a diagrammatic representation of maximum likelihood estimation. So on the x-axis here we have plotted pi ranging from 0 to 1, and on the y-axis we have plotted the value of the likelihood. Note that the value of the likelihood peaks at the point corresponding to the dotted line, and this point and its projection on the x-axis is the value of the maximum likelihood estimator for this example. More generally, the likelihood for the data is given by L of pi. More generally, the likelihood of the data is given by L of pi conditional on the data is equal to pi to the power x into 1 minus pi to the power n minus x, where we assume that we have observed x successes. The log likelihood function is given by log of L pi equal to x log pi plus n minus x times log of 1 minus pi. The score function is given by d log L pi d pi equal to x over pi plus n minus x into 1 minus pi into minus 1 equal to x over pi minus n minus x over 1 minus pi, and setting this equal to 0 we get pi hat equal to x over n. By plotting the function or by calculating the second derivative, we find that this indeed corresponds to a maximum, and thus the maximum likelihood estimator is given by the sample proportion x over n. Maximum likelihood estimation is popular due to certain desirable properties of the estimators. The first property is that the estimators are consistent under some very general regularity conditions. Note that this means that they are asymptotically unbiased. Indeed, we need to stress on the use of the word asymptotically because maximum likelihood estimators can often be biased in finite samples. One general example is that maximum likelihood estimators of variance parameters will have the divisor 1 over n, and we know that this is biased as compared to the sample variance with divisor 1 over n minus 1. Another desirable property of the maximum likelihood estimator is that it is asymptotically efficient. This means that it obtains the minimum variance in asymptotic situations. It is also possible to derive the asymptotic distributions of the maximum likelihood estimators, and these can be shown to be normally distributed. A further desirable property is that in such situations where a sufficient statistic exists for the parameter under estimation, the maximum likelihood estimator will be a function of this sufficient statistic. The asymptotic variance of the maximum likelihood estimator is calculated from the information matrix. So if we assume that the parameter is specified by alpha, I of alpha is equal to minus of expectation del square log L alpha del alpha square. The asymptotic variance is given by the inverse information matrix. We can also define the likelihood ratio corresponding to a distribution. So minus 2 log of L alpha hat, where alpha is some pre-specified value and alpha hat is our maximum likelihood estimator, is equal to twice of log of L alpha hat minus log of L alpha, and it is well known that this follows a chi-squared distribution and can be used for the purposes of inference. We have assumed here that alpha is a single scalar parameter. These properties can easily be generalized to the case where we have a vector valued parameter. An automatic consequence of using maximum likelihood for estimation is that we have a ready-made testing procedure. So say for example, we have a scalar situation where we have a single scalar parameter and we wish to test H naught alpha is equal to alpha naught for some specified value alpha naught. This can be done using Wald's test statistic, which is given by Z equal to alpha hat minus alpha naught by square root over V alpha hat. Alpha hat here is the maximum likelihood estimator of alpha, and V of alpha hat is its standard error derived from the inverse information matrix evaluated at alpha hat. The statistic Z follows a normal distribution with mean 0 and variance 1 under the null hypothesis alpha equal to alpha naught. A second option is the likelihood ratio test, and this is given by minus twice log L alpha naught by L alpha hat equal to twice of log L equal to twice of log L alpha hat minus log of L alpha naught. So for the case where alpha is a scalar valued parameter, we know that this will follow a chi-square distribution under H naught with 1 degree of freedom, and hence can be used to test the hypothesis alpha equal to alpha naught. Chromatic representation of the three tests. The Wald statistic is looking at the differences between alpha hat and alpha naught standardized by their variance. On the y-axis on this graph, we have plotted the value of the log likelihood, and the likelihood ratio test is looking at the corresponding differences in the value of the log likelihood. The score function is given by the derivative of the log likelihood, and thus we are looking at the significance of the tangent of the likelihood evaluated at alpha naught. In general, for large data sets, the three procedures will lead to very similar estimates. Chromatic representation of the three tests. The Wald statistic is looking at the differences between alpha hat and alpha naught standardized by their variance. On the y-axis on this graph, we have plotted the value of the log likelihood, and the likelihood ratio test is looking at the corresponding differences in the value of the log likelihood. The score function is given by the derivative of the log likelihood, and thus we are looking at the significance of the tangent of the likelihood evaluated at alpha naught. In general, for large data sets, the three procedures will lead to very similar estimates. Let us look at a fundamental likelihood which we shall use several times in this paper, and this is the multinomial likelihood. You know that the multinomial likelihood is employed in the situation where we have a categorical outcome. If we assume that we have C categories, then the log likelihood is given by L pi equal to summation over j nj log of pi j, where pi 1, pi 2 to pi c are the probabilities of belonging to the C categories respectively, and summation of pi 1 to pi c is equal to 1. To find the maximum likelihood estimators in this situation, note that del log pi c del pi j is equal to 1 over pi c del j equal to minus 1 over pi c. Thus, in vector form, del L pi del pi j is equal to nj pi j minus nc by pi c is equal to 0. This means that the maximum likelihood estimator obeys the relationship pi j hat by pi c hat is equal to nj by nc, and using the restriction summation of pi j hat equal to 1 equal to pi c into summation nj over j by nc equal to pi c hat n by nc, where n is the total sample size, leads to the maximum likelihood estimators pi j hat equal to nj by n. This means that the corresponding sample proportions for the various categories are the maximum likelihood estimators in this case. You are all familiar with the Pearsonian chi-squared statistic. We have seen the statistic in various forms. For now, assume that we wish to test a hypothesis of goodness of fit. That is, pi 1 naught, pi 2 naught to pi c naught are specified values of the category probabilities, and we wish to test the simple hypothesis pi naught h naught pi I is equal to pi I naught for j equal to 1 to c. You all know that the chi-squared statistic of goodness of fit is given by chi-square equal to summation over j nj minus mu j squared by mu j, where mu j is the corresponding mean frequency for the various categories under the null hypothesis. This can be used as a test for goodness of fit, because under h naught we can expect the statistic to be small, and in case of a lack of fit we expect the statistic to be large, so that we can have a right tail test based upon the chi-square distribution. The Pearsonian chi-squared statistic turns out to be a special case of maximum likelihood based inference. Note that by virtue of properties of the maximum likelihood estimators, root over n pi hat minus pi naught follows normal 0 sigma naught, where sigma naught is a matrix with element sigma jk equal to minus pi j pi k if j is not equal to k, and pi j into 1 minus pi j if j is equal to k. This follows from the multivariate version of the properties of the maximum likelihood estimator. Wall statistic, that is a multivariate version, is then given by the quadratic form n into pi hat minus pi naught prime sigma naught inverse pi hat minus pi naught. And I leave it to you as an exercise to show that this form of the statistic is indeed another way of representing Pearsonian's chi-squared statistic. In this module, we have reviewed the concept of maximum likelihood estimation. Maximum likelihood estimation is a very popular technique for statistical inference. The reason it is so popular is because the estimators have some very desirable properties. Now note that these properties mainly hold for asymptotic situations, and in finite samples, maximum likelihood estimators can be seen to have some drawbacks such as bias. However, an additional reason why they are so popular is that the moment we specify the likelihood based on some very general regularity conditions, we are automatically available some methods of inference such as Walls test, score test, and the likelihood ratio test. So we have reviewed these tests in this module. Finally, we have looked at the multinomial likelihood and also derived the well-known chi-square test of goodness of fit as a special case of a Wald test using maximum likelihood estimators.